circular motion review. When something spins in a circle, it has to be experiencing a force that keeps it moving in a circle. If I were to spin a ball around on a string in a circle, that ball would have the desire to move in a straight line path on its own. This is what we would refer to having tangent velocity. Its speed would want to travel straight. But because it's being pulled into the center of that circle, it has to follow that elliptical pathway. If I'm pulling something into the circle, then I must be feeling a force. This is what we refer to as a centripetal force. And if I'm being pulled in by a force, then I'm going to have an acceleration on that object as well. From my equation, force equals mass times acceleration. So we have centripetal or center-seeking forces and acceleration. And our velocity is trying to maintain its inertia and stay in that outward path. So we have that tangent velocity. Equation-wise, if we want to find the force, we're still following our mass times acceleration. Now to find the acceleration, that's the velocity squared divided by the radius of that circle. So force could also be said as mass times my velocity squared divided by that radius, because that's how I find my acceleration. To find velocity, we're looking at the fact that you're traveling in a circle. So our distance is the circumference, 2 pi r, divided by the time that it takes to travel that circle. Here it's a capital T to represent the period, and that's the time for one rotation. In terms of equations, whenever you look at an equation, think about the function y equals x. They're both on the top. That's a direct relationship. If we were to graph y equals 1 over x, this shows an inverse relationship. My y is on top, my x is on bottom. So if I can learn to apply that rule to every equation, then I can see some pretty distinct relationships forming. So my force is going to be directly related to both my velocity and my acceleration. That means that more velocity equals more acceleration and more force. And my acceleration is the same part as my velocity. If I look at the lower half here, then I can see that these are opposite of each other. This is an inverse relationship. Here, if I have a bigger radius, then I experience less force. If you've ever tried to take your car on a hairpin turn, if I take a big turn with my car, then I'm not going to experience as much force. It's easier to go fast. If I try to take that same car really, really quick in the same speed, then I'd go flying out, hydroplaning. So here, because they're opposites, we see that inverse relationship. More radius gives us less force, and as a result, less acceleration. Or smaller radius would give us more force and more acceleration. Things that commonly travel in circles are planets. The Earth is traveling in a circle around the sun. It's being pulled in towards the sun. And that pull towards the sun is what we call gravity. We can calculate how much gravity any two objects exert on each other, so the sun pulling on the Earth. We're even thinking about the Earth pulling you towards the center of it. To do that, we use what we call the universal gravity equation. So our universal gravity equation is going to be the universal constant, which is just a value that we use to make the equation work for every mass that we've ever come into, times two masses. One mass would represent the Earth and the other the sun, or the Earth and you. So I have my two masses for the two objects that are being pulled into each other, divided by the radius, or the distance between them. So how much space between the Earth and the sun. between me and the Earth. Because I'm a lot closer to the Earth, I'm pulled towards the Earth. I'm not being pulled off into outer space and into the sun. That would just be weird. Again, let's look at those relationships. Here, on top, we have a direct relationship. Because it's a direct relationship, if my mass increases, my force is going to increase. And if both of my masses increase, then my force would increase by that much. So if I double my mass, then I double my force. If I double two masses, then I'd quadruple my force. Tripled my mass, triple my force. Triple times triple will give me 9 times. If we look at the lower half, we have that inverse relationship. So here, if I have a larger radius, then I experience less force. Think of it like a relationship. If Tommy and Susie are in the same school, they tend to like each other a whole lot more. But when Tommy moves away, Susie's very likely to start liking Bob. Less distance between these two means there's a bigger connection. Here I've got more distance, a little less of that attraction, like gravity. Let's look at some examples of this one. Here my radius is being squared. So it's not only an inverse relationship, it's what we refer to an inverse square relationship. So here, if I double my radius because it's squared, I already see 2 squared, 4 times the change. So I've got 2 times more radius, I get 4 times less force. If I did 3 times my radius, again 3 squared, 3 times 3 is 9 times the change. If I cut my radius in half, use a calculator if you need to, but 0.5 squared is 1/4, or 0.25, 4 times the other direction. So here I'm experiencing less change. If you don't like fractions, then we can think of it as here we had more radius, less force. If I'm getting less radius, then right away I can know I'm going to have more force. So I can still look at that fourth and just recognize that it's the opposite relationship. So 4 times the force. I know that I've got 3 here, 9 times. If it's more radius, I get less force. If it was 3 times less radius, I get 9 times more force.